So all participants welcome for the third session. Shortly we will begin the session. The speaker for the third session, Dr. Asim Tiwari sir, is shortly joining for this session. Uh,
Good afternoon,
yeah,
everyone.
welcome sir, welcome. Yeah. So just a brief, I will tell you about the program, sir. So we had today two sessions in the morning. First
Uh-huh.
session was conducted by Dr. Guru Prasad Rao, and he discussed about like the past, the present, and future about the 3D printing, and also talked about the design engineering. And the second session we had by Dr. Karuna Karan sir, and sir
Uh-huh.
discuss about the various activities which he has conducted in rapid manufacturing lab, various the additive and hybrid manufacturing processes which he has developed in his lab. He has shared about that. So he has talked about like this disruptive technology in this present era. So okay, that's all about like how this is where the program is placed now.
All right.
Yeah,
Excellent.
yeah. So shall we start, sir? Are we ready?
Absolutely.
Yeah,
Absolutely.
just give a time, 1 minute, sir, for the organizers to introduce you. So,
Yeah.
organizers, over to you.
Yes, sir. A very good afternoon to one and all present. I welcome you to the third session of this 1 week faculty development program on 3D printing and design, sponsored by All India Council for Technical Education's Training and Learning Academy under Azadi Ka Amrit Mahotsav and IQAC SPCE. It gives me immense pleasure to introduce you to our today's eminent speaker for this session, Dr. Asim Tiwari sir. He has completed his PhD from Georgia Institute of Technology, Atlanta, USA, and his MS from Georgia Institute of Technology, Atlanta, USA. He has completed his BTech degree from Indian Institute of Technology, Kanpur. Dr. Asim Tiwari sir is G.K. Devrajulu Chair Professor in the Department of Mechanical Engineering at Indian Institute of Technology, Bombay, Mumbai. Prior to this, he was a staff researcher at General Motors Global R&D Center in Bangalore. At IIT Bombay, he has been instrumental in setting up the National Center for Aerospace Innovation and Research and Center for Technical Textiles. He has also been co-investigator in Biomedical Engineering and Technology Incubation Center and Center for Excellence in Steel Technology. He has established several advanced state-of-the-art facilities, including Advanced Machining Excellence Cell, Fiber Composite Research Laboratory, 4D X-ray Microscopy Laboratory with capabilities of in situ thermomechanical deformation, an experimental lab for the thermomechanical simulation and nano characterization texture laboratory. He has also established a research group in smart manufacturing, machine learning, data analytics, and IoT for various sectors, including manufacturing, transportation, and defense. His personal area of research is in mathematical models for microstructural mechanics. He has over 100 international journal and conference publications and 10 international patents. His pioneering work in 3D microscopy has been widely cited, including reproduction in ASM handbooks. He is on the editorial board of several international journals, including Metallurgical and Materials Transaction and Image Analysis and Stereology. He is an advisory committee member for various national and international research boards and has won several awards and recognition for his research and teaching. Today, Sir will be talking on the topic additive manufacturing A logarithms. So now I request Dr. Asim Tiwari sir to kindly commence the session and we warmly welcome you, sir.
Well, thank you very much. I had been thinking as to what would be the most appropriate topic to talk about today to you. And the key aspect is that I was looking at the demography of all of you. And many of you are senior faculty at various colleges and universities and engineering centers. Many of you are students, doctoral students, research scholars, and of course, undergraduates and master's, postgraduate students. So I see a very diverse, I would say, group here. And in a diverse group, it's always a little challenging to present something which is meaningful to all. At the same time, it's not trivial to others. So I just was thinking that maybe so far what you have, and I knew the schedule, I saw what was being done before. And then I decided that probably I will get into something a little more specific, which you can take with you. So I have about 2 hours. And in these 2 hours, I want to make you a different person. I want that after these 2 hours, there should be something which should become a part of you. Every time when you look at any such phenomenon, which I'll be talking about today, you should be in a position to understand it a little more intimately than what others are able to. So I don't want to just give you information. I don't want to basically just provide you a Nat Geo and Discovery kind of things. I don't want to give you a very high level overview. I don't want to get into the micro details of the scientific stuff which my group is doing, because all of these will be either too generic for you or too specific that you would not be able to appreciate it. So I want to spend this time to create an understanding which you can take with you at every step. So bear with me, 2 hours is a long time. And I want to not just talk about that, I want to give you other senses as well. So certainly I will give you information as well. But the basic idea is that we should be able to have a clearer understanding with the underlying phenomenon. And the phenomenon which I want to talk about today is residual stress. So if by the end of these 2 hours, you stick around and you don't sleep in between, and I don't make you sleep in between, then I'm hoping that by the end of these 2 hours, you will be able to critically analyze any situation which produces residual stresses, and you will be able to not through equations. I will talk about equations, but you may not become conversant enough with the equations, but you will be able to reason it out in your head as to what to expect when a phenomena of that kind happens. So that's the basic idea. So the usual drill, I want to start by very quickly. Let me just see. I'll just share my slides now. Okay. So I'll just start by sharing my screen so that you are able to see what I'm saying. So now you guys see what I'm talking about. And essentially, I'm going to talk about algorithms. But essentially, it's a very generic topic. Algorithms for what? And there are tons of different things which I could talk about algorithms about. I have slides which are primarily made by my 2 doctoral students and my research associate. So Deepak Soman is my doctoral student, and Vinod is my research associate, and my colleague, Professor Sushil Mishra. So I'm using those slides. Before that, I'll just quickly tell you as to what do we do in our labs, in my lab, and the various activities which we do in all the activities of research which I'm involved in. So I do a lot of stuff in composites area, which is polymer-based carbon fiber and glass fiber composites based on simulation and modeling of the process, to the manufacturing of composites through vacuum-assisted resin transfer molding, to autoclave, to 3D printing of composites. And I'll talk a little bit about that. So additive manufacturing in composites is also what we do. Then do tomography, 3D tomography, look at the microstructure in 3D, do machining and post-processing, and also finite element analysis-based life estimation. Another very big area of research in my group is in machining. We do all sorts of machining, be it milling, turning, drilling. We have instrumented 5-axis machines which can measure forces, torques, temperatures, vibrations, acoustic emissions while you are performing the machining operation, and thermal imaging. And you can look at that and create an understanding of how machining is happening, what are the underlying mechanisms. We have a lot of experience in machining of titanium alloys as well as machining of super alloys, Inconels primarily, and Invars. So this is another very big activity. We may not be really talking about it today, but just good to know that such things are being done. Another very big area which my group is involved in is in smart factory and IoT and ML. So machine learning and aspects associated with the Internet of Things has become an integral part of our daily lives. So we have an entire group which is developing newer smart IoT devices which are installed on various systems. They send real-time data to the cloud, and the cloud performs machine learning-based analytics on it. And a very, very growing field. I'll say this is something which is growing more fast than anything else. And these are just to show some of the aspects which we are involved in machine learning aspects. And then finally coming to additive subtractive machining. So we do additive manufacturing and subtractive manufacturing. What you see on the top left is a EOS machine for powder printing. This is a part of the BITEC program, the Biotechnology Incubator Program, which is headed by Professor B. Ravi. This is a machine which was developed by a PhD student of Professor Karunakaran. And you spoke to, and you heard him in the morning today. And I very closely collaborate with him. And we have, I'll just come back. And we are in the process of procuring this machine. It should be here by March of next year. It should be actually installed. We are expecting it to be with us in Feb. And this is a 5-axis additive subtractive machine, which means that you can do an addition as well as subtraction right in the same machine. And this has capabilities of both powder as well as wire feed. And we can pretty much do any alloy. We can do aluminum, titanium, nickel, iron, even copper has been tried on it. This is with a laser source, and this is a directed energy deposition based system. This is, of course, not our machine. What you see is a representative image, but our machine is going to be here by 2022. And these are the various things which you can achieve on that. And as I was showing, that you have a powder feed as well as you have a wire feed. And the beauty about wire feed is that wires have lesser surface area, at least like 5 to 6 orders of magnitude lesser surface areas. And because of that, actually 10 orders of magnitude lesser surface areas. And because of that, they do not get contaminated by oxygen. So if you are doing powder-based additive manufacturing, you need to create a very high quality inert atmosphere around it. Whereas in a wire feed, you really don't need that, because wire has very less surface area and you can really get a very high quality part with very little environment around it. Of course, we will be having an inert environment around it, but what I'm trying to say is that that would not be so much of an issue if we are having a wire. The other big advantage of wire is that your volumes which you can deposit are far higher. So you could have a far higher volumetric deposition rate. And these two things make volume wire feed a very good process for the additive manufacturing. Now, as I said, we are not just into additive manufacturing of metallic parts, but we also do that of composite. So we have 3D composite printing capability. And this is just to show you some of the carbon fiber composite parts which have been printed, 3D printed. And on the right-hand side, you see 3 parts. These are the brake levers. And what you see is that they have different colors. I don't think if you can see the middle one, but the left one is of course all white and the right one is all black. And actually the middle one is in between these two. And what really is differing is that you have very high carbon percentage on the right one side. You have a little less carbon in the middle one, and you have no carbon in the leftmost side. So these 3 are the same exact geometries by varying carbon fraction, going from 0 to the maximum, which is about 35%, 40%, which we can achieve in this case. And this has been created using additive manufacturing. So we can actually print carbon fibers, Kevlar fibers, glass fibers, even high strength high temperature glass fibers. So there are many different fibers which we can add and print. And of course, there could be many other complexities which you can build about around it. Now, coming to the aspects of what I wanted to talk to you about today is residual stress, which is one of the biggest challenges for additive manufacturing. So let me start by a very great story, a real life story, which my center was involved in, NCR. And this is the drilling-induced distortion. Now, I would like you to not listen to this as something which is just, a presentation going on, but I want you to spend some time and try and understand what I'm just showing you right now. This is a very exciting detective novel, in a sense, I would say. You're trying to understand what is going wrong. What I'm showing you is that there is a tube which is kept, if you can see, it's made up of titanium on the left-hand side. This is the tube. This is titanium tube. This is before machining. We take this tube, we fix it on this fixture, and as you see this fixture, we fix it on this fixture, and then, let me get a laser pointer. So we fix it on this fixture, and then we do the machining of this. So now you can simply understand, we have this part, it's a hollow part of titanium made by forging and by metal, processing. And then we put it on this fixture, and then we do machining of this. So now you can see this fixture goes into the CNC machine, and this is the CNC head, which is having the drill tool, and we are drilling holes in it. When we drill holes in it, everything is perfect. Then when we take it out, now this has holes in it. But once we take it out, we see that it has opened up by 20 mm. Now this is a real life problem. Can anyone think why this is happening? And of course, I've pretty much given you the clue, because I talked about what I'll be talking about today. I already told you that. But what is happening is you have this part. This part is taken to the CNC machine, and after drilling holes, when you take it out of the fixture, you realize it opens up. Now, why is this happening? This is literally like a mystery which you don't understand why. So what happens is that if you think about drilling, what you realize is that you are basically having tensile residual stresses and compressive residual stresses. And both are essentially, in this case, tensile. So you have tensile residual stresses outside and tensile residual stresses inside. This is slightly distorted for some reason, but anyway, you understand the point. So this has tensile residual stresses both outside and inside. And what is happening is that now, because of your machining, you are removing the material, you are removing part of the material which is outside, and you are removing that from inside as well. And in doing so, you are basically, let me just try and see if it does that. Okay, forget it. I don't want to change that. Let me just stick to what I have. So now we have residual stresses both inside and outside. And in the initial case, they are both balancing each other. So the residual stress outside in the periphery of that pipe and the residual stress inside the periphery are exactly balancing each other. Why are they balancing each other? Because it's a residual stress. There's no external stress, right? So they have to balance each other out. And since they balance each other out, there is no distortion. It's just like that. It remains like that. Now what happens is that when you see what is the length inside, you realize that the inside arc is smaller and the outside arc is larger in perimeter. Since the outside arc is larger in perimeter, inside arc is smaller in perimeter, the inside has higher stress density due to smaller circumference. So the stress is exactly, the total forces are same, but stress per unit length inside is more as compared to that outside. Now this is unique understanding. Once we drill holes, hole is essentially a constant diameter region going from outside to inside. So hole removes equal amount from both inside and outside. Now this is the hole. Once the hole comes in like that, what happens is that the total force now is unbalanced. Why? Because you have removed the same amount of material from outside as you have removed from inside, but the inside had a higher stress density. There was more high stress per unit length as compared to outside. Now, because of that, what happens is that since you have removed that material, you've removed more material inside for the stress level. So the same amount of material is removed, but that material had higher stress. So you have removed more stress from inside as compared to outside. And that leads to the opening of this. So now the stresses are no more balanced. So outside has a higher tensile stress, outside has a lower, has a higher tensile stress as compared to inside, because you have removed some of the tensile stress from inside and more than that from outside. What I'm trying to tell you is that residual stress is a very complex phenomenon which happens in almost every aspect of processing which we do. And we need to have an understanding of what is the underlying mechanism of it being created and how to mitigate it. Otherwise, you will never be able to work with that. So let me come back to additive manufacturing. And I'm just showing you again two competing technologies of AM. One is the direct energy deposition, DED technology on the left-hand side, and the powder bed fusion technology, which is on the right-hand side. And we performed experiments on the same alloy for both DED as well as fusion bed. And we wanted to see how does the microstructure look. And this is how the microstructure looks. And of course, there's a substrate. And on top of the substrate, we have the deposited materials. The substrate has a slightly different microstructure from the deposited material. But the material has somewhat similar structure, though the exact coarseness and other things would vary depending upon our process window. Now, once you see this, you can, of course, take the same thing to more complex cases of Inconel, which is another very big area which we focus on. And what you see is that there are specific signatures of layer change. So this is the first layer, this is the second layer, this is the third layer. And as you go, you see these lines. These lines are showing you that there's a change in layer which is happening. And that is happening because your rate of cooling for the top layer when you add within that layer and the bottom of that layer is different. So when you deposit the next layer, once the next layer gets deposited, the surface which is in contact, the bottom surface of that layer has a higher rate of cooling as compared to the top part of the layer. And that really leads to variations in microstructure. And there is, of course, leading to variations in chemical composition, which is what I'm trying to show you. Iron, nickel, chrome, niobium, and moly, how they are changing as a function of the space. And you can see that. Now, moving forward, finally, we are looking at these samples from the structural tensile point of view. And we want to see how will they perform in a structural loading. And that's why we performed various process variations and produced these parts and performed a tensile test on them. And this is just to lay the basic background. I don't want to get into the experiments which we have done, but this is one of the experiments which would be of interest, and that's why I'm talking about it. So now what happens is that this is the, I hope I'm still visible and audible.
Yes, sir. Perfect.
Okay.
Yeah.
Okay. All right. Yeah. It showed that I have lost some connection, but anyway, okay. Please feel free to ask me questions if you have also. So don't just hesitate stopping me. So what we see is that these are the tensile tests of various parts made by additive manufacturing. And of course, what you see is not just a macro image, but it's a very fine microstructure image, which has been compressed together to give you this. So if you see there are checkered, pattern, which you can see, and that is because these are all collections of lots of images put together. But one of the key things which is very clear is that they have a lot of porosity in it. And of course, we didn't try to do anything to reduce porosity. We just went with it as it was. So now that is something which is very obvious from this. You can see black spots here, black spots here, others you can't see yet. But if you start looking at the fracture surface, so what you can do is that once the sample fails, you can look at the fracture surface. And once you look at the fracture surface, you can start seeing the evidence of porosity on the fracture surface. And if the fraction of porosity on the fracture surface is more than the fraction of porosity in the cross section of any plane, then it means that your crack, your surface, which is the fracture surface, is following porosities. And thus porosity is getting bridged and you're forming a fracture surface. And that is what we see in almost all these samples, that porosity is playing a dominant role in leading to fracture. So that's why we realize that one of the biggest challenges in additive manufacturing becomes porosity. And porosity, of course, triggers fracture. Now, another very strange thing which we have seen is that there are lots of cracks. If you see this, you can see this crack coming on this. So these are additively manufactured parts through directed energy deposition, Ti-6-4 and other materials. And what we see is that you start having these cracks coming in them. Now, this is very strange. Why would a crack come? A crack means what? A crack means that the material broke. But it usually breaks when we put it under tensile test. Here we have not done any of those things. So why is it breaking? And that's where we realize that it is breaking because there are internal residual stress. There are internal stresses which make the material crack. So the two biggest shortcomings of additive manufacturing for the property are porosity and cracks, which essentially is coming because of residual stresses. Of course, surface finish is another big issue, that you don't get beautiful surface finish as you get in machining. And that's why we are going for additive subtractive machining. So our machine, which we are about to install, is essentially an additive subtractive machine, which will be doing both additive part as well as machining right on the same structure. Now, having said that, we have many other issues also, which are really very challenging and are very, very interesting. Those are primarily the CAM issues in additive subtractive machining. For instance, the geometrical complexity, cutting tool accessibility, multi-bridge structures and overhangs. How do you handle that in additive manufacturing? How do you perform a part decomposition? If you have this cup, do you want to just decompose this as one part, or you want to take this part separately, you want to take this part separately? So how many parts will you make this in? What would be the built orientation? Now, this is something which matters a lot. Because imagine if you have this cup and if you're building everything like this, then what you realize is this handle, which is turning, would have all right built here, but once it goes to the curve part, you'll start having overhangs. And thus the built orientation becomes an issue. These things cannot be done on a design by design basis. There has to be an inherent algorithm which will automatically provide a solution to these problems. Now, in 5-axis additive manufacturing processes, directed energy additive manufacturing process, your bed itself can be tilted in any direction. So when you're doing any deposition, you are in a position to turn and tilt it in any direction, and thus you essentially can create any orientation which you like, and thus the built orientation is not so much of a constraint, which essentially means that you have a far more versatile possibilities of built orientation. And that's a very challenging thing, because now you could have built orientation for each subcomponent different. And thus you need to figure out what should that be and what is the most optimal one. Adaptive slicing. Now that's another very, very important thing. You don't want all slices to be of equal thickness. Some would be thicker, other have to be thinner. And it all depends upon the complexity of the underlying geometry. Deposition path using open source additive files, AMF is an additive manufacturing format which we have based on XLM. But there are many other possibilities of improving on additive manufacturing file format, AMF. You could come up with more complex file formats, and which are being right now looked at. So all the information of the process may also be contained in the file format for additive manufacturing. And thus you don't have to give any process information separately. And your additive manufacturing unit, your printer should be able to read that directly and set all its parameters to make sure that it provides us the best additive manufactured part. However, having said that, I don't want you to feel that these are areas which are not being looked at. These are very actively worked on areas, and people are having a lot of research happening in this area. So now let me jump on to a little more technical. So far it was all very generic things which we have been doing, what we are planning to do, what we can do, and things like that. So now let me talk about something completely different. Continuum mechanics. And now you may think, why am I just talking of mechanics? Now the reason I'm talking of continuum mechanics is because additive manufacturing, and I'm talking of metal additive manufacturing, is a very, very complex process. Why? Because it has a lot of different kinds of physics which are taking place at the same time. So your heat source is heating the base and is causing it to melt. At the same time, you're adding an external material, which could be either a wire or a powder, and that wire or a powder is being fed. So there is some kind of a dynamics associated with that. It's being fed into the liquid metal pool, and thus there is a churning effect which you are happening in the liquid metal pool because of the addition. However, at the same time, there is a convective heat loss. There's an environment of air around it, an environment of inert gas around it, which is being flown by you. So there's another heat loss because of that, and thus there is a momentum transfer and heat transfer, which is a coupled problem. At the same time, the weld pool or the melt pool where you're adding the wire or the filament is also having a churning happening because it's just a pool. It is colder at the base, hotter at the place where the heat source is coming from, and that would lead to churning of the liquid inside that melt pool as well. And that adds to the complexities. Then you have a phase transformation occurring. The phase transformation is because of solid going to liquid and liquid again coming back to solid. Even within solid, there could be many phase transformations. You could have martensite formation when you do very fast cooling. You will have when you're heating, ferrite becomes austenite. Austenite, once cools, becomes again ferrite or could become martensite. You could have alpha titanium become beta titanium and vice versa. So there are a lot of various things which can be envisaged. And continuum mechanics is one of the key understanding physics, one of the key physics required in all of this process. So the key physics which you required is mass transfer, momentum transfer, heat transfer, and continuum mechanics. So if you have all of these taken care of, then you essentially can handle any of the problems. So this is the very basic equation of continuum mechanics. And don't sweat over it. It's very, very straightforward equation. What it is saying on the left-hand side is that the first derivative of a stress plus the body force Fi is equal to 0. Of course, this is assuming that the body is not having an acceleration. So this is with an inertial frame where the body is either in rest or constant velocity. So what it says is that the gradient and stress is directly is equal to minus times the body force in it. This could be, of course, written in a more compact form like this. This is the basic equation of physics, which tells you that if this body is in equilibrium, this is what should be happening. Then comes the geometrical understanding or geometrical definition of strain. So this is epsilon ij, which is equal to half of del ui by del xi plus del uj by del xi. Now this is your equation which relates displacement to the strain. So this is the strain definition. Strain is equal to this given by displacement. And then strain is related to stress by this equation. So stress is equal to stiffness times the strain. Of course, this has been written in the complete form. So we are talking of the stress tensor being equal to the L, which is the stiffness tensor, fourth rank tensor multiplied by the second rank strain tensor. So this is the entire, these three equations put together give you the entire quantum mechanics of elastic bodies. That's it. You don't need anything else. It's just now specific solutions of this for plates, for beams, for discs, and all those things will be different. But otherwise, the basic equations will remain the same. And similarly, now you have the definition of this, a basic equation definition also now contains the definition of strain given by compliance as a function of stress, which is nothing but just the inverse of it. And of course, to solve this set of equations, which you realize now are differential equation, you would also require some boundary conditions. And these are the boundary conditions which they have. So you could have a zero displacement, or you could have a displacement boundary condition, which tells that how is the surface of your system going to be displaced because of these actions. And the other is saying that there is a traction boundary condition, which says what are your surfaces and what kind of traction they are getting. So these are the two possible boundary conditions. So once you have all the things in this, you essentially can solve the problem. What are all the things which you need? You need the force F, you need the value of L or M, which is a material property, and you need the value of Ui as a function of a space, or the as a function of space on the boundaries, or the traction on the boundary. So displacement and traction on the boundaries are the two other things which you need. So now this can be all put together and you can make a concise form. So the same three equations could now be written in a much more concise manner, which is just saying that this is equal to the body forces coming in. This can be solved, and I don't want to go into the Green's function solution for it, but this can be solved, and we are just solving it for a special kind of force, F, which is such that it tends to become zero when you go to infinitely far away from the origin. So that is basically Fi goes to zero as x1 square plus x2 square plus x3 square tends to infinity. So this is the only aspect which we are solving right now. And if you do this, you can solve the previous differential equation, and what you'll get will be something like this. This is the Green's function based displacement field. Now I've talked a lot about a lot of things, and I don't think you'll be able to follow this completely. But now is where that was the basic requirement, but now is where we come with the basic understanding of the term eigenstrain. So if by the end of the day today, you are able to understand eigenstrain, and you are able to understand that eigenstrain relates to residual stress, then you'll be able to figure this whole thing out. So what did we say? At a very, very coarse level, we said residual stress is a big problem in additive manufacturing, which leads to cracking. The additively manufactured parts can crack because of residual stresses. Those are internal stresses which break it. Because we talked about stresses, we need to talk about solid mechanics. So I told you and I showed you some equations of solid mechanics. After having showed you some equations of solid mechanics, you'll say, where are residual stresses coming in that solid mechanics? I just had a stress is related to strain by stiffness. That's it. Basically, no big deal. So now I'm going to introduce a concept, and next 3 slides are, I think, the most important slides. So feel free to stop me, and I have like another 80 slides. So those are not so important slides. I will be sharing all of this with you. So you will have those slides. But the next 3 slides, this and the next 2 slides, are the most important slides. This is where your concept of a new term known as eigenstrain is going to come. Eigenstrain is a generic name given to any inelastic strain. So any strain which is not elastic is called eigenstrain. So can you suggest me possible ways of eigenstrain? The answer is yes. You could have eigenstrain as thermal strains, phase transformation strains, initial strains, and I don't want to elaborate, but initial strains could be hopefully from an eigenstrain. Misfit strains. So any strain which is having an origin other than elasticity is an eigenstrain. So can you visualize that? Now I'll come back to this slide, but let me just quickly go to the next slide and show you that I have an unconstrained heating and cooling occurring for a part. So this is a part which is free. This is a cylindrical disc which is completely free from all sides. I heat it up and I cool it down. So basically this is just showing me the temperature variation, And as you heat it up and cool it down, what would happen? As you heat it up, it will expand. As you cool it down, it will contract. But in this entire process, it expands and contracts, which means it has a strain, but it has no stress. There is no stress associated with that. You just had this body freely expand. That's why I'm calling it free, right? So it's a body which you heated up, it expanded. It was a free expansion. So a strain happened. Why? Because there's a displacement of the parts of the points on the surface of this, and the displacement of every single atom of this happened. However, it doesn't lead to any stress. So what you realize is that the displacement here is because of the coefficient of thermal expansion, and because it was unconstrained, it expanded as much as it wanted. But in doing so, it did go through under a strain, but not stress. So if I go back to this relation, which is relating stress and a strain. So this is strain and this is stress. But in this case, what happened? We had a strain. The material expanded, but there was no stress. Now what do? This equation is no more right. Stress is equal to stiffness into strain. There was a strain, but there was no stress. How is that possible? Anyone? All right. Afternoon, after lunch may not be the best idea to talk about these equations probably. So what you realize is that the strain which you had, which we called as eigenstrain, need to be subtracted from the total strain. So this is the total strain. Total strain is made up of two parts, eigenstrain and elastic strain. So what we just now saw was that there was an eigenstrain, which is a strain because of inelastic region, which was expansion because of heating. So that was the eigenstrain. Since there was no constraint, the material was allowed to expand freely, which means the total strain was also equal to the eigenstrain, which means the elastic strain was zero. And stress is not related to strain, but stress is related to elastic strain. So I think this is the main understanding which you need to have. So stress is only related to elastic strain, and elastic strain is the difference between the total strain minus the eigenstrain. And in this case, the total strain was exactly same as eigenstrain. Because it was totally same, the elastic strain was zero. And since elastic strain was zero, there was no stress. Is that clear? Are you guys understanding what I'm saying? Anyone?
Yes, sir.
All right. Now I will change the thing. And what I'll do is that now I will have a part which is not allowed to expand. So if you see, it's no more free. It is fixed from both the sides. So I have a cylinder which is fixed from both the sides now. Now, since it is fixed from both the sides and I'm heating it up, what would happen? If I had heated up, yeah, tell me what would you expect? Do you expect it to expand?
No, there will be restrictions. So expansion will be not permitted. And because of that, stress will be developed.
Absolutely. So you would expect an expansion because it is fixed. You will not allow expansion to happen. And because expansion will not happen, it will lead to stresses. So now you can break this in your mind in two ways. The first one was allowed to expand freely. Because it expanded freely, there was no stress at all. In this case, you just fixed it and you didn't let it expand when you heated it up. And because of that, what happens is that there will be a lot of stresses which will be there. Now, to better understand it, imagine the fixed case is made up of two parts. So rather than just fixing it and heating it, imagine you let it free. So it expands freely. After it has expanded freely, now you press it and bring it back to the original state. So if you look at the original state and this state, you will feel as if it is fixed. So the fixed heating can be thought of as a process where you allow it to expand freely and then you compress it and bring it back to the same fixed state. And since it has come back to the same fixed state, it should behave just like the one in which it was always fixed to start with. So if it was fixed throughout the process, should be no different from the one which was free in the beginning, allowed to expand, then you compressed it and you brought it to a fixed state. Which means that now you did have an eigenstrain which was exactly equal to the expansion. But in this case, the eigenstrain was such that you had to bring it down to make the total strain 0. So this eigenstrain was still the same, whether it was free or not free. But in the first case, E was 0 because this was exactly same as the eigenstrain. In the constrained case, this is 0 because you're constrained, no expansion possible. That's why E has to be minus eigenstrain. So that is the basic understanding which you need to have, that in the free case, the elastic strain was 0, the eigenstrain was exactly equal to the total strain. In the fixed case, the total strain is 0 because you have it fixed. And because the total strain is 0, that's why the elastic strain has to be equal to opposite the sign of the eigenstrain. And what is the eigenstrain? Eigenstrain is the strain because of the expansion of this because of heating. So eigenstrain is always a strain which comes from a physics other than the heat expansion physics. So it is coming it comes a strain which comes other than the stress analysis physics. So the stress analysis and the solid mechanics is not adding anything to the eigenstrain. So the eigenstrain could be either because of coefficient of thermal expansion, phase transformation, twinning. So there could be many plasticity. So there could be many other things which are beyond the scope of your continuum solid mechanics. Of course, you can add this as a part of solid mechanics, but it's essentially coming from some other physics. So that strain will be provided to you by some other physics. So this quantity, which is eigenstrain, is given by another physics. In this case, that physics is coefficient of thermal expansion physics, but it could be something else as well. Is that one thing clear? All right, I hope it is. So now I want to show you that this is how the stresses are changing, basically, and this is the heating and the cooling cycle and things like that. So you essentially go through a whole process of heating and cooling. Now what happens is that if you do heating, it may expand so much that when you have, because since you have it fixed, it may yield. If it yields and now you cool it, it may actually become smaller in size. Now that's one of the key aspects which you need to realize. Another very simple thing which you need to understand is that the average stress in a volume, and in this case, the entire sample or anything, is given by if you have a traction boundary condition. So this is the boundary condition. If I say that there is a force which is being applied on my system from outside, which is given by epsilon ij not nj, which means that this is a force in the I direction. So if I'm applying a force in the I direction in this case, then what I will realize is that what I will see is that I will end up having a body which will have an average stress given by this stress tensor. Sigma ij not nj is the force which I'm applying in the I direction. Okay. Now what you need to realize is that if the sample is under a traction boundary condition given by this force, then the average stress, internal stress of the body integrated over the entire volume, is given by this quantity. Why am I talking about this? I'm talking about this because in a residual stress, there is no traction. It's a traction-free boundary condition. There are no external stresses. Since there are no external stresses, this stress is 0. And that's why the average stress in a residual stress, if it is a residual stress, then the average residual stress in a body is exactly equal to 0. So that's the underlying reason why your average stresses are 0, which means that if you have a tensile stress somewhere else, you will also have somewhere a compressive stress, so that the volumetric average of all those stresses become exactly 0. And that is one of the key aspects which you need to appreciate. So with that, let me now talk about what all are the key aspects which play a role in the formation of residual stress. So there's a transition, which is a moving heat source, and that moving heat source would lead to a transient solution, and that is something which could create a complexity. It is essentially same in welding, which is what I'll be talking a little more in depth about. Phase transformation, you could have ferritic to austenite, austenite to liquid, liquid to austenite, austenite to ferrite, perlite, martensite, bainite, tempering of martensite and bainite. So all of these solid state and liquid solid transformations could lead to a change in the eigenstrain and thus leading to the stresses. So the eigenstrains could be because of phase transformation, could be because of solid liquid transformation, could be because of thermal expansion, could be because of constraints from the outside, and they can also change the entire strain, not the eigenstrain, however, because eigenstrains don't really care about the external constraints. So this is a very simple model, and I will be talking about a more complex part of it when we get into the finite element based modeling of this. So this is a very, very simple 3-bar model, which is very often used in welding. What this model says is that how the welding is going to result in residual stress. The question is, when you're welding two parts, let's say you're not adding any filler material for the sake of simplicity. Let's just say you're just heating a part, and that part gets heated up, then it melts, then it solidifies, and that's it. Now, you expect it to have residual stresses. The question is that, do you really expect it to have residual stresses because you heated it up from room temperature to high temperature, and then you cooled it down from high temperature back to room temperature? So you've brought it back to the same place where you started from. And if you've not added any material, should it still have residual stresses? And the answer is yes. It will have residual stresses provided when you heated it up, it did not go to a place where there were irreversible transformations which happened. So let me just talk to you about what is happening. So this can be handled by this 3-bar arrangement. Your bar 1, bar 2, bar 3. These are just to show you how this material is being modeled. So we are having the welding gun go from here in the center. And when we do that, the center part will essentially get molten, and the other 2 bars will just get heated up but will not melt. Now what happens is, and I'll just show you here, maybe I'll show you in the 3-bar first. So just imagine if you have 3 metallic bars which are joined here and joined here, or welded here, let's say. Now if you start heating the center bar, what would happen? If you take a torch flame and just heat the center bar, now what happens is the heating of this will make it expand itself. At the same time, the other 2 will also become warm and they'll start expanding, but not to that large extent. Now, this expansion is essentially nothing but an eigenstrain. And because it is constrained from the top and the bottom, and these 2 sides have not expanded enough, thus this top and bottom black region will cause a constraining effect. So the center rod is trying to expand, but is being constrained. And since this is being constrained, it will lead to compressive residual stress in the central rod. It will have compressed residual stresses, whereas you will have some kind of a negative residual stress. Opposite to composite, it will be tensile residual stress. So what you will at other places. So the center rod is now trying to expand, and because it's not being allowed to expand, it gets compressive residual stresses. The other 2 rods which are holding it back get the tensile residual stresses. So the center is in compression, these 2 side regions are in tension. Now you keep heating, so which means that this has more high temperature than the sides because it's centered, the heat source is centered. And that leads to eventual melting of the center part. And once this center rod melts, what happens? Initially, when you heated it up, it started expanding. Since it could not expand, it got constraints, and thus it developed compressive residual stresses. But once the liquid melts, there are no possible stresses which a liquid can handle, and thus the liquid starts flowing, and you now have 0 stresses. Why? Because the central rod is completely molten and it cannot transmit any stresses because it is a liquid. And because that is a liquid, the other two supporting rods don't have to push anything further as well. So the moment you have melting of the central rod, all the residual stresses disappear. All the stresses disappear. I won't say residual. It's not yet residual in that sense, if I may say. So all the stresses disappear. Now remember, these two rods have also expanded because they were also heated up, but not to that large extent. So the expansion of the middle was the highest and the expansion of materials away from the middle was less. Now having done that, and now the central rod being formed as a liquid cannot sustain any stresses, so it loses all the stress and the liquid flows. And because the liquid flows and there are no stresses, the two rods on the side also then become without any stresses. So the entire stresses are lost the moment you get a liquid in the central rod. But we are not done with it yet. What now we are doing is that we are going to cool it down. When we cool it down, the liquid in the central rod will now freeze and solidify. Till it is liquid, it is all right. But once it freezes, it can now again start exerting stresses. But now what you realize is that the liquid from the central rod has flown away when it expanded and more got molten. And now once it is being frozen, it's probably having a much less material. And thus once it is frozen, it shrinks. And that shrinking is more than what the expansion actually happened. And that is because it has less material now and it is shrinking. And there were no stresses. So it starts shrinking. But again, these two rods are not letting it shrink. Since those two rods are not letting it shrink, it is trying to shrink, but it's being held together. So it will form a tensile stress inside it. And since it will form a tensile stress inside it, these two sides will have a compressive stress. Probably I've been speaking a lot. You hopefully get a picture. What I'm trying to say is that this is how the temperature variation and stress variation will happen. If you are at a far away place, AA, there are no temperature variations. You have not yet reached over there. The weld gun has not reached there. The heat source has not reached there. And that's why AA has no stresses. So there is no stress and no delta T. Delta T is also equal to 0. Once you start coming close to it, what happens? The delta T starts increasing and you are at a BB section. So in this section, you are having the center expand more than the rest. And thus you start having a very high stress in the center, and those center stresses have to be compensated by stresses of the opposite side on the sides. So you essentially have a compressive stress in the center and a tensile on the sides. And this is how it becomes. However, when you are at this location, so when you are at location B, which is this right on the pool, what you realize is that at the location B, the stresses in the center are exactly 0. Why? Because everything has become molten. And then when you cool it down, you come to CC, this line, and what you realize is that now the temperatures are coming down, but now the center has started having a tensile residual stress. And by the time you're far away from it, the center develops a tensile residual stress and the regions besides it have compressive residual stress. Remember, going up is tensile residual stress, going below is compressive residual stress. And there is no temperature. It is still at room temperature, which means it has gone back to AA. So what we are doing is we are looking at AA, then we are looking at BB where the melt pool is there. We are looking at CC a little behind BB. And then we are looking at a very far away region, which is again back at room temperature. And this is how the residual stress variation has happened. Now, had there been no melting in the central pool, then we could have avoided residual stresses, but not always. Why? Because residual stresses didn't happen just because of melting, but could have also happened because of plasticity. And that is another more complex aspect beyond the scope of today's discussion. So coming back now, this is how the residual stresses in butt weldeds vary. Residual stresses vary like this. Now this is a very important aspect. Effect of temperature and time on stress relief in steel welds. Now welding has a lot of literature, and all these problems of porosity and residual stresses and distortion exist in welding. Additive manufacturing is actually nothing but a more glorified welding topic. Now over there, the effect of temperature and time on residual stress is very important. Why? Because once you expose a welded structure or an additively manufactured structure to temperature, for a high temperature at a high enough time for a long enough time, you'll start seeing that the stresses decrease themselves. And why do this happen? This happens because of many mechanisms, and one of them is that the heat is provided, the sun is providing it the heat basically, and then the sun is providing heat, which is leading to what has happened. So what is happening is that you are having heating, and the heating is causing, sorry about that, the heating is causing the atoms to move, and the stress goes through a stress relieving process. So the temperature exposure at a long enough time causes the heat to relieve residual stress. And there are many mechanisms involved in there. Plasticity is one. Why? Because when you heat it up, the plasticity of the material falls down, the yield stress falls down. Another mechanism is that you have creep, in which the material starts flowing because of creep. You also have a stress relieving because of dislocation movements. Your dislocation mobility increases. So a lot of things happen which lead to reduction in residual stresses when you expose something at a high enough temperature for a long enough time. And these are some of the soaking times which we do in steel for stress relieving. Now, I'll just quickly talk about what kind of distortions do you expect. And this is something which you must have by now understood. If you have seen those 3 rod case, you should be able to see how the residual stress would lead to distortion in this. So if you look at this plate, what you'll realize is that the center has been welded, and it has been welded from the top. And since it has been welded from the top, it will eventually, once it cools down, it will create a compressive, it will create a tensile residual stress in the center. And the tensile is trying to pull everything down. And because of that, your actual plate, which was flat, will become distorted like this. You can think of the same for a T-joint, and a T-joint will also lead to that kind of distortion. And how would the distortion be affected by the thickness? Of course, if it is very, very thick, you lead to large distortions. What are distortions, by the way? The distortions are nothing but the stress relieving of the residual stresses. If the stresses are so asymmetric that they result in distortions, or distortion happens when the residual stresses are asymmetric. And the moment you take it out of the fixture, the residual stresses being asymmetric relieve themselves, leading to distortions. So a distorted material has fewer residual stresses, but of course the geometry is unacceptable. So if you have a very thick part, it will lead to larger distortions. If you have a very, very thin part, the distortions will be much less. And this is just to show you how the filling and other things will change. Now this is for welding, but not very different things will happen when you start looking at additive manufacturing, and that's where the strategies of additive manufacturing come into play. So this is just to show you how various strategies in welding are being changed. So you're adding a material here, then adding material here, then all adding at the one side first, and then adding on the other side. Whereas here you are adding once below, one stop, once below, one stop, and what you realize is it has much less distortions. Now, this is something which you need to realize, that having no distortion doesn't mean that you have no residual stresses. As a matter of fact, you could have more residual stresses, and you are likely to have more residual stresses if you had distortions. This can, of course, happen in more complex geometries. I don't want to go into these details. You could actually design it such that you start with a slightly deformed part, and when you weld it or you join it, it leads to the final designed shape after having going through distortions. Of course, fixturing and preheating is another thing which you can do. And these are some of the aspects of showing how the angular change is leading to different kinds of distortions. Now, coming back to additive manufacturing. So we talked about residual stresses coming from the mechanics of eigenstrains. You have I hope, an understanding of what eigenstrains are now. Eigenstrains are inelastic strains, and they are responsible for residual stresses. Of course, the stresses finally have to come from the elastic strains only. So if you let the material expand or distort freely, then there will be no residual stresses. However, there will be eigenstrains. If you constrain it or you self-constrain it, then it would lead to elastic strains, which is nothing but the total strain minus the eigenstrain. And that leads to residual stresses. Residual stresses can be mitigated by heating, by heat treatment, and by strategies of additive manufacturing. Now, this is just to show you one specific case in which we are adding material layer by layer through our additive process. And these are the individual pieces which have been generated by additive manufacturing. And you can see the layers as you go from one to the other end. And we can now measure the microstructures. And this is what is showing you some porosity there. This is showing you a microstructure variation, fine microstructure, coarse microstructure, huge porosities. This is how the grains, individual grains look. And they are, of course, distorted and elongated. You can also see variation in hardness. So when you measure the properties, you see a variation in properties. Texture is varying a lot depending upon where you are adding. Some parts, the grains are equiax. Some parts, they are very elongated. You can have the macro texture looked at it, which is the crystallographic orientations, may not be something which you all understand. But what is most important is what I just wanted to bring out to you, which is these residual stresses. Now you can measure the residual stresses by X-ray diffraction. And there are many other ways in which you can measure residual stresses. So when you are doing additive manufacturing, the part may look very nice and good, but it will have residual stresses. And you need to measure those residual stresses. So this is just to show you some of the normal residual stresses measured and some of the shear residual stresses which are being measured. They have been measured using X-ray diffraction in our labs. These are the actual numbers in MPa. Remember, these stresses cannot go beyond the yield stress. Why? Because if they go beyond the yield stress, yielding will happen. So no stresses can go, no residual stresses can go beyond yield stress. So that's the basic idea behind the residual stresses. And of course, the microstructure would accordingly show variations. So then coming to as to find, once we have this, what does this tell us and how can we now model this? And that is where the main challenge comes. So essentially what you are having is that we need to perform a modeling, and I'm just showing you one aspect, and then I'll get into a slightly more detailed aspect of what do we do in terms of understanding and exactly predicting these. So what you're seeing is that as you are heating and you're having a heat source which is moving, the heat source is never a flat heat source. You have more heat at the center and less heat at the sides. In our case, for instance, if we have a laser source, usually a laser source have a Gaussian heat profile, which is what I'm showing you over here. Highest temperature, highest heat per unit area at the center, and as you go further away from the laser heat source, though the spot size could be, let's say, 1 mm or 2 mm, but that 2 mm is not having the entire 2 mm as the equal heat. You are having very high heat at the center. So you need to model that. Then you need to model the heat transfer, and I'll talk about that in a second. So you need to now model many other things apart from the heat source. But heat source is one of the key things which you need to certainly model. Once you have modeled the heat source, you need to do the thermal modeling. So you need to do a thermal modeling of the entire part which you are additive manufacturing on. And finite element is now very advanced in doing thermal modeling as well as the structural modeling. I just showed you the equations which you need to solve for the structural modeling. Now remember, the regular finite element packages are not necessarily trained to handle eigenstrains and residual stresses creation. You can introduce residual stresses. Is there a question, or is someone? If there is a question, please ask me. Otherwise, you could just mute yourself.
Yeah. Leela, ma'am, you have.
Yeah. Okay. All right.
Yes.
Yeah, that's okay. Yeah. Please. Yeah. So you can have finite element analysis based thermal and structural modeling performed, in which you are solving the heat transfer equation, and you're solving the solid mechanics at the same time. And this need not be fully coupled. This need not be fully coupled because you are not really having.
Leela, ma'am, please unmute your mic.
I think the organizers can mute them also, so you don't have to point out any.
Yeah, I will do the needful. Sir.
Yeah. So there could be some problem. I know that it happens when you're having these things happening. You could get unmuted accidentally. So the finite element can be used to model both the heat transfer and the thermal aspects as well as the structural aspect. And they need not be fully coupled, which means that the heat transfer can happen independent of the structural modeling. The reason is that the heat transfer is not a fully coupled model, which means that the heat transfer is not being changed because of any structural variation. However, structural variation is certainly changing because of heat transfer. So this is a one-way coupling of heat thermal modeling to the structural modeling. That makes life much simpler. So this is what we validated for welding and additive manufacturing, and I'll show you some of the simulations. So you have thermal fields, you have heat transfer model, which leads to thermal fields, and those thermal fields leads to strains. And those strains based on constraints at the boundary, if it's a no traction or no displacement boundary, will lead to stress strain fields. So this is the overall aspect of the modeling of the stresses and the thermal aspects. However, apart from stresses and thermal aspects, what you realize is that there is also a phase transformation which can happen. So now this is understanding residual stresses from the finite element perspective. You can see stresses on the left-hand side and the temperature on the right-hand side. And as you see, as the temperature is increasing, actually the stresses could fall, could increase. So there are a lot of different things which could happen. Now, what you need to realize is that and I'll just take you to the next slide, that this entire process is having one-sided coupling from heat transfer model to the solid mechanics model. But the solid mechanics model is also being coupled with the phase transformation model. When you have austenite formation, there's a volumetric change. When there is a martensite formation, there's a volumetric change. And these volumetric changes will create eigenstrains leading to residual stresses. So you need to model them at the same time. So now let me just quickly tell and show you the complexity which comes because of the phase transformation modeling. So this is what is happening in terms of phase transformation. So you are having a materials model, especially in this case for maraging steel, and this maraging steel is now going through austenite to martensite phase transformation, which is following this expression. And what you see is that this is the model and this is the experimental. Blue is the model, red is the experiment. And as the temperature is changing, the material expands, but then suddenly goes through a reduction and then again goes to expansion. Why is this happening? Because this is martensite in the beginning, and the martensite is expanding with increase in temperature. The moment you reach a temperature at which martensite transforms back to austenite, which is given by this expression, it becomes austenite. And austenite is a FCC material which has a lower cell volume, higher density. Martensite is the body-centered tetragonal, which has more volume per cell and thus less density. So it's more voluminous. So the moment it forms austenite, it goes through a reduction in volume, and thus the strains fall. So what you need to realize is there's a thermal expansion which is causing these strains to grow, but there's a phase transformation which causes this strain to fall. Then of course, if you keep heating it up again, now the newly formed phase of austenite goes through the coefficient of goes through a thermal expansion leading to this. So this is the heating cycle. Now the cooling cycle is more interesting, because now you are cooling and you have an austenite, so it goes through a cooling cycle because of thermal contraction now, but it does not form a martensite right away. At the time at which the martensite changed to austenite, at that temperature you don't form martensite when you're cooling, however, and there's a hysteresis involved in this. And that hysteresis means that you will have an austenite up till a lower temperature, almost 200 degrees C, and after that you suddenly will form martensite. And as you form martensite, which has a lower density, it will expand. So suddenly you'll have a strain increase. So what I'm trying to tell you is that now you have a process of heating, a heat transfer process. The heat transfer process leads to thermal expansions, but you also have phase transformations of solid phase transformations going from martensite to austenite and austenite to martensite. And thus all of these put together will lead you to your eigenstrains. And this is having a hysteresis, which means if I just tell you this temperature, you can't tell me what strain would it be, because it will depend upon history. If I started with martensite and I heated it up and I'm at this temperature, then I will have this strain. But if I started with austenite and I'm cooling down, then at the same temperature, I'll have a lower strain, which means that you need to know the history also, not just the current state, to know the entire eigenstrain. And all of this eigenstrain, depending upon the boundary condition, will lead to residual stresses. So that's the bigger picture which you need to understand. Now, once you put all of these things together into a finite element model, you essentially will be able to get something of this kind, which will tell you how the temperature is varying and how the melt pool is varying, and thus go next and see how the temperature fields are varying and how the stresses are varying. Now, this is essentially a simulation of a single heating, moving heat source, a single streak of a heat which is there. In this case, to validate this, we used welding. Why welding? Because welding is well-known process. You can very nicely instrument it, and a single bead of addition of a weld material is same as additive manufacturing. If you do multiple of them, it becomes your additive manufacturing. So now we can perform this by various multi-passes, not just one pass. So we can add one pass, two pass, three pass. So we are adding multiple passes here, in this case, 3 passes. And in each pass, when you pass and add and do that again, the temperature of the substrate is no more the same. So the temperature has slightly heated up because your previous pass had heated the material up. And you can come up with very, very, very complex strategies of how this will happen. And now what you realize is that the temperature is also causing the properties to change. So as you heat the material, the yield stress falls, the elastic stiffness falls, the Young's modulus fall. And thus you have to take into account all these complex things at the same time. Not just the heat transfer and the eigenstrains, but the stresses also, because the stiffness is changing. And stresses are related to strain by the stiffness, right? So now if you put this is how the actual residual stress variations can be seen on individually added sections. Now for this, what we did was that we performed actual experiments in bulk V grooves, and we added the material in a welding process. And this is probably the most, I would say, authoritative experiment where we were actually adding welded material step by step and keeping track of how that welded material is changing the temperature, how that welded material is changing the distortion and stresses and everything. So what we did in this case was that we constrained the plates from the side, and we had thermocouples all over the place. which could measure the temperature at different locations of the base metal. And then we had a thermal camera on top, and that thermal camera was capturing the temperature. So what you see on the left hand side are actually the thermal camera images of this material when you are actually doing the welding on it. So these are not simulations, these are actual experimental data. And based on the emissivity of the material, which is, by the way, a non-linear function of temperature, you would be able to create the actual temperature maps of what really happened when you were doing that single addition. So you have now an experimental way to measure the actual temperature which is formed while you are adding a single bead. And the same can be, of course, done through simulations. And when you're done through that, when you do the same through simulation, you can see how the temperature variation is actually occurring. So you can exactly see the temperatures from this and this, which is simulation, and map it with the experiments. What I'm trying to tell is that we now have a very powerful experimental tool which is used to validate our multiphysics numerical models which we have developed. Now these two put together would provide you the understanding of the residual stress formation. Now going beyond residual stress, now what this can be used is now that you could use this for many other purposes now. So you could use it for purposes like understanding what should be the total amount of heat extraction which you need to do. You may also want to use it for instance, to see how much of cooling you need to have to not have a part which is sensitive part become heated up. You could also look at it and see what kind of strategies of build you need to have. So what kind of hashing strategies you need to build, for instance, which could be used for minimizing distortions or minimizing residual stresses. So now it is up to you to figure out what really you want to do with this. But essentially, you have all possible ways in which you can create the process variables and optimize them to get the exact structure, get the exact weld details which you want, and all of those. So now let me show you how we use this, and let me just see if I can go to the next slide. Where's my slides now? Yes. So now I want you to see how we use this to go and create a very complex build strategy. So now this is the actual experimental thermal values which we calculated. And then we looked at how the residual stress would be varying. Now this is where we have added about 20 odd layers going from one to the other. And these are the layers which are being added one after the other. Build strategies could be different. You could add 1, 2, 3, 4 all over here and then add on the other side, or you could add few here, then there, and vice versa. And what you see is that the residual stresses are now a function. So this is basically looking at residual stresses on this, along this line and along this line. So we are looking at on the two sides. So these are those two curves. One is for one side, the other is for the other side. And what you realize is that the two are not exactly the same. If this line is very, very close, the residual stresses are higher. If this line is taken further away, the residual stresses become much closer to zero. But what you need to realize is that they are not symmetric top and bottom. So the top is not exactly an inversion of the bottom, and the two, which is on this side and on the other side, are also not the same. So you are creating some very unique asymmetries in your sample when you are doing additive manufacturing. And you could look at each of those individual parts which you've added and figure out which would be the most appropriate thing to handle this. Now, what also you get are some very unique microstructures, and I want to talk about that a little. But before that, I want to talk about now that this, what we did for welding, is now being used for powder bed as well as directed energy deposition, additive manufacturing. And now the aim is to essentially have an entire model where we can change the power, we can change various build strategies and see how it is changing. So now this is to give you the hashing strategies. You could have all of them built layer by layer, each layer having the same direction, or you could have them rotated by 90 degrees. So you have one layer deposited like this, the other layer deposited like that. And you could have all sorts of combinations in which you could change the orientation of 90 degree also. So you have it deposited like this, then like this, then like this, and then like this. So you could have many different build strategies, all generated in the computer. And this is what we are doing right now. So we are adding layer by layer material based on our build strategy, based on our power, based on our velocity and all those things. And we are seeing how is the temperature varying and how is the residual stress varying. So this is something which needs to be done before you actually start building the models in your machines. And the reason is that in the machine, it's number one, very expensive to do that. Number two, in the machine, you don't have a way to measure residual stresses right away. And because they are internal parts, and that's when it can lead to distortions and cracks internally, but you won't be able to measure those quantities which you could do it in these simulations. So these are some of the leading algorithms which we use, which is a combination of eigenstrains for solid mechanics, phase transformations, heat transfer, and phase transformation. So all of the solid state phase transformation and liquid state phase transformation. And all of this put together leads to a clearer understanding of how the residual stresses are being formed. Can they lead to distortions and can they lead to cracking? And this can be used to optimize the additive manufacturing process, because it's an open question. Now, the other part which I talked about, which was the part of the porosity. So I want to now quickly talk about, so there were two major aspects which I said additive manufacturing have an issue. One is distortions and residual stresses and cracking, all because of distortion and cracking because of residual stresses. The second is porosity and the microstructure. So I want to quickly talk about some aspects of the complexities which you can get in a microstructure. And what you need to realize is that when you are going through a process of welding, your microstructure really goes through a very, very complex process of let me just try and see if I can pull that for you so that you can appreciate as to what is happening in your welding microstructure and what is happening in your additively manufactured microstructure. So what I'll just do is that I will show you the complexities which you could have when you are going through additive manufacturing process, because your structures are very quickly changing from one state to the other state to the third state. And that is where a clearer understanding of what is the underlining, what could be the underlining phases and how would they play a role in your overall additive manufacturing becomes very important. So let me just quickly switch gears to this, and I hope you can still see my slide, or no, you can see my old slide. I'll probably have to stop that and again ask you to see my new slide, which should be seen by you now. So now what is happening is that I think it's slightly hanging up. I hope you can still hear me because my computer shows it's hanging. Is anyone able to hear me?
Yeah, sir. Yeah, we can hear you, but slide we can't see.
It's not coming. Okay. Yeah. Because it's just gone into a hanging mode. Screen is frozen, but let's see. Let me try and get out of this maybe and see if that helps. Too many presentations open at the background. I think that could be another reason. it's not able to figure out which to show. Let's see. No, I think I'll have to just log out and log in again because the screen is frozen. Let me just start another instance. Just give me a second.
Okay, sir, no issues.
I'll stay on this. I think I can start 2 instances simultaneously. Or maybe not. No, okay. So I'll just have to log out for a second.
Okay, sir, okay.
It's not even letting me log out.
Sir, you are on mute.
All right, so now I can share my screen again. And this is what I wanted to share. And I hope you are able to see it now. Yes, it's there.
Yes, sir. Yeah.
Now you will be able to see. So now I wanted to bring out the other complexity. So unfortunately, in mechanical engineering, majority of time, we are just interested in how the thing looks from outside. Whereas what matters the most for a performance is what is inside that, which means the complex microstructure which you have. So when you look at a steel, you don't just look at a steel, there are multiple phases inside: ferrite, austenite, cementite, martensite, bainite. When you look at an aluminum alloy, you say, oh, this is aluminum. No, it's not just aluminum. It has multiple phases. It has alpha aluminum. It has, eutectic, pre-eutectic aluminum. It has silicon particles. It has other precipitates. Or all those individual phases inside it essentially are the ones which are responsible for the properties of the product. Now, in conventional processing manufacturing, we do casting, forging, forming, machining, heat treatment. We essentially give all of these individual components, individual manufacturing processes, their due, I would say, diligence. But in additive manufacturing, all of this has to be done in one shot, in one single step, which is of the additive manufacturing. And that's where you realize that you are doing the solidification, forming the final shape, and the heat treatment, all is happening at the same time. And since you are constrained by the shape complexity, you are not really performing the solidification as you may want to do otherwise. So what I want you to appreciate is that depending upon how you are coming, you will have segregations which will happen. So if you think about this composition C0, when you're cooling down, your liquid will be initially at this temperature where the first solid will form and the final solid will be this. And thus you'll have a gradient in your composition. So the solid will not be always of the same composition. And depending upon the rate at which you're cooling, you could have different kinds of no diffusion and complete liquid diffusion, no solid diffusion and complete liquid diffusion, to no solid diffusion and limited liquid diffusion. All of these things can happen. And this is how the chemical profile of the solid and liquid would vary. So you need to have an intricate understanding of the entire process of solid solution partitioning and solute partitioning in the phase diagram to be able to appreciate that. And this becomes paramount when you are having very fast solidification. Everyone wants to build very fast. Now in additive manufacturing, since you are adding only a small amount of material, you could actually have a very high rate of cooling happening as well. And that could lead to more complexities. So your solid phase could have a compositional variation. liquid could have another composition variation. And when you are having a melt with another solid in its vicinity, which happens in your welding and is also happening in your additive manufacturing, then you start having a growth, which is an epitaxial growth. And that epitaxial growth is leading to the liquid metal growing on the previous layered grains. So the new layer, when is added, it grows on the previous layers, and that's how you start having these grains grow on the previous layers. And this is something which is dictated by the crystals of the previous layers. But those crystals of the previous layers are very soon, and I'll skip some of these, are very soon taken over by the competitive growth because of the orientations. So now what is happening is that the direction of your build is dictated by the geometry, but that also dictates the gradient, the thermal gradient, and the competitive growth starts happening because of thermal gradient and the orientation of the individual grains. So you start having some very, very complex microstructures of this kind forming. Now this is a single weld bead which is going, depending upon the speed of it, if it is very high speed versus if it is low speed, the structure of the grains which are being formed could vary. So what you now need to understand is that not only is the distortion and residual stresses important, and that can be mitigated by your process variables, but also your process variables will have an immense effect on the underlying microstructure. And thus, you need to optimize your process variables, not just to create residual stresses to be low, but also for a specific microstructure. So now if you see, this is telling you what is the individual grains and why the grains are growing like this. The grains are growing like this based on the competitive growth between thermal gradients and the orientation. And this could be the other aspect where you have, so now this is for almost a pure metal. For a pure metal, there is only single phase. So it's a liquid and a solid. So liquid solid has almost no gap. Whereas for an alloy, there is a gap, a melting region, right? Which is where it is both liquid and solid, which is the mushy zone. So the solidus and the liquidus temperatures are different. So when you go from a single alloy, a single element to an alloy, which is now, so the previous one was almost pure aluminum. Now when you go to the same, to an alloy, that alloy will lead to a slightly distorted, a different kind of microstructure. So the same process window for a pure metal versus an alloy versus another alloy, depending upon the range of solidification, you could create very different structures. And just to give you that within the pool itself of liquid metal, when you are actually having this go through, there will be temperature variations which will occur. So this is the direction of movement of your heat source. This is the pool which is formed. And this weld pool or the liquid pool, melt pool, will have different temperatures at different regions. So this is the fusion line, which is where this is liquid. But this is not liquid. Outside is not liquid. So if you see, the center line temperatures are going like this. This is how the fusion line temperatures are. And you have partially melted regions in between in this. So this is the partially melted zone. Beyond this, complete melting. Beyond this, complete solid. Under this, complete melting. This is the mushy zone. The gap between the liquidus and solidus. So this is the temperature in which you will be having both solid and liquid. So once you are forming a single bead in your additive manufacturing and going forward, within the melt pool, you have large variations of temperatures, and those large variations of temperatures lead to large variations of phases. So you have solid outside it, complete liquid inside that, and in between you have a mushy zone. Now, having said that, it's just a mushy zone is not sufficient. Why? Because you are actually also having a very large fluid flow which is occurring in these liquid melt pools. Now, the previous modeling which I showed you was a macro modeling where we were ignoring these. But we also do this modeling in which we look at the individual melt pool model. We look at how the fluid is flowing in the melt pool, and how is the temperature transfer, heat transfer happening in one weld pool. And this leads to three different mechanisms. There's a dendrite fragmentation mechanism, grain detachment mechanism, and the mechanism of heterogeneous nucleation. All of them put together would lead to different structures. So you can see these individual microstructures which are getting formed, and they are forming because of the three previous mechanisms which I talked about, which is the dendritic fragmentation, grain fragmentation, and heterogeneous nucleation. And these can be used to explain all of these structures. Now, in this structure, what you see, you are having a further added stray field. So while performing additive manufacturing, you could actually add a magnetic stray field for stirring. So additive manufacturing is still a very big growing science. You are not just doing things by just adding layer by layer, but you can do many other aspects of things around it at the same time. And one thing which you can do is that you can create stirring in the melt pool at the time of additive manufacturing. And this is showing that on the top, you are having no stirring, and in the bottom, you add an electromagnetic field to stir the liquid metal in the melt pool while you were doing the additive manufacturing. Now, this is something which has phenomenal potential for additive manufacturing. Why? Because the biggest challenge of additive manufacturing was porosities and coarse microstructure. That can be completely taken care of this. So now what you realize is that you have two problems in additive manufacturing. One is cracking and distortion because of residual stresses. The other problem is because of porosity and poor microstructure. Now the distortion and cracking is because of residual stresses, and you can mitigate it from a macro model. However, the porosity and the microstructure can be mitigated by the micro model. And that micro model will essentially lead to some specific changes which you can cause and at the melt pool level, which will lead to better microstructures. Whereas at a macro level, the strategies by which you add material, the hashing strategies will lead to lower residual stresses. So you are actually, in a sense, controlling the additive manufacturing process at two levels. At a hashing strategy, at macro energy, deposition and deposition strategies is leading to changes in residual stresses. And then some handles, for instance, like residual stress, EM stirring, leading to microstructural changes. And these two handles you have to take into account to be able to create the final microstructures and the final residual stresses. So what I'm trying to say is that there is a lot which can still be done, and it still needs to be done in the AM field before we really say that now AM is able to do something great. This is to show you the pulsed arc welding process, in which you are essentially having an electromagnetic stray pulse which are being created, and these are oscillatory electromagnetic fields, and they create a unique microstructure of their own. So what you see is that this is a very unique microstructure, and they will have far superior properties than just a simply additively manufactured microstructure, which is what you had seen so far. Now, all of these new developments, when added to additive manufacturing, they can create additively manufactured materials which are far more strong and are having far less distortions as compared to the regularly additively manufactured materials. However, unfortunately, these developments are still not streamlined for the manufacturing processes. So you can't really buy a machine which will let you do this kind of an additive manufacturing right now. But the kind of research which we are doing, both in terms of modeling and experimentation, we are introducing these and creating the I would say new age additive manufacturing, where we are incorporating different kinds of additive manufacturing processes in the field itself, in the machine itself. So just to show you an example, one more example, and I'll just show you.
I think it will be this. So this is something which my colleague Professor Karnakaran did. This was a process in which he started using a hammer, a pneumatic hammer, to impart, mechanical distortion, mechanical work on the additively manufactured part. So this is a hammer, a pneumatic hammer, which is causing hammering to the newly additively manufactured layer. So this is a kind of a thermomechanical treatment, mechanical treatment to the additively manufactured layer. The same can now be done by having a very high induction coil, which will do the mechanical metal stirring, electromagnetic stirring of the metal. Of course, that is only possible for cases where the metal is ferromagnetic. If it is not ferromagnetic, it would not be possible to stir. But essentially, these are some of the latest advances which one needs to understand to be able to appreciate the growing field of additive manufacturing. Now, the other area which I didn't talk about, which is where we are interacting with a company for additive manufacturing, is the role of single crystal growth. What I showed you a little while back on the epitaxial growth of the additively manufactured part, what happens is that we can use this same concept, and I'll hope I'll be able to share again with you. We can have the same concept of epitaxial growth used to create, and I'll just share this. Yeah, we can use the same concept in a completely, entirely different space. So we can use this epitaxial growth. So once you have the next layer in additive manufacturing added, the melt which is formed when it starts solidifying on the same crystal which was there of the previous layer. So that is the epitaxial growth which we can have over here. The epitaxial growth which we can have. So this, you can see the previous grains are what are growing. Now, this is something which is being used very successfully in additive manufacturing for repairing of single crystal gas turbine blades. Now, these single crystal gas turbine blades are a single crystal. The entire blade is made up of one grain, but it may get chipped off due to some usage and all those things in engines, in, of course, gas turbine engines, jet engines. So you take these blades out, but they are very, very expensive to make. So you don't want to throw them if they have just a small chipped out part. What you can now do is that you can use additive manufacturing to grow the same grain epitaxially. So the single crystal grows back again, and you have a single blade made up of a single grain with no chipping anymore there. And you can machine it finally after that, once you grow that grain, and then you get the right finish. So this is another very big process which is being used right now for additive manufacturing. So now coming to the last challenge of additive manufacturing, which I feel is the biggest challenge, which will stop additive manufacturing from becoming the only process for all manufacturing, is the cost. You cannot have very large volume productions, and they're very expensive. And that's why they are very expensive. So in forging, you can have a cycle time of 15 seconds, 20 seconds. Stamping, you're just stamping one after the other. You could have an assembly line which could go through that process. Machining, gear machining, not so small, cycle times, but within 3 minutes, 2 minutes. In automotive world, 2 minutes cycle times are very commonly seen in machined processes. But additive manufacturing will never have that fast cycle time. And that is why it will never be able to replace the conventional manufacturing processes. However, this will have its own niche areas where the conventional manufacturing processes are either very slow or just are not available. And the first biggest place where it will be used, and which is currently being used, is in the area of repairs of turbine blades. Another area where it is being used is in the area of repair of dies and molds. So you may have a very big die and you just get some cracking or you get some part which is broken. Then you don't have to throw away the die, which is very expensive. You can just do additive manufacturing on that, recreate the broken part, and then machine it and create the final surface. So that I feel is the biggest challenge, that you cannot have very high cycle times in additive manufacturing, leading to very large costs. However, the cost is coming down except for the time, and thus additive manufacturing will find its applications in places where it will be low volume or customized. And customized, another very big area of customization is implants. An implant area is one area where every individual is different, and thus you want a separate implant for every individual, and that's where you can actually use additive manufacturing to create those implants, because you can't have a mold and a die made for every individual. It will be just way too expensive. That's another niche area where additive manufacturing will become very big. And finally, in closing, in the last part, the part of additive manufacturing becoming very big are cases where you don't want very large inventory, or you may not be in a position to keep a very large inventory. So just imagine you are on a ship and you have some 5,000, 50,000 different moving parts in it, and they can break. But you don't want to keep the inventory of all the 50,000 parts. You just need a 3D printer and the metal powders, and you can just print whatever part breaks. This could also be the case when you want something on demand. For instance, in a war, you are in the field. You don't have the logistics to get a part from the factory. You just print it over there. Or for that purpose, you could be sitting in Mars or Moon, and you can't have a flight from Earth to Moon or Mars to fetch you a part. So if you have a part which is broken, you can just print it. So what I'm trying to now going to say is that there are a lot of different kinds of challenges with additive manufacturing has. I didn't talk about CAM challenges. I did briefly touch upon it, like part decomposition, build orientation, and slicing strategies. I did talk about the two major challenges, which are the microstructural challenges, porosities and microstructure not being good, and the distortions and cracking because of residual stresses. And hopefully now you have a slightly better understanding of what residual stresses are, and are in a position to at least understand them from a physics perspective. And then, of course, you need to look at models to be able to mitigate residual stresses. These are macro models, which look at build strategies, hashing strategies, the rate at which you are depositing. Whereas the microstructure has to be modeled at a weld pool level, where the pool-based models are looking at how the microstructure is changing. And over there, you can have handles of the kind that you can cause mixing in the weld pool and thus create all the microstructures. And all of these put together will finally lead you to the final part and your additively manufactured part. And the sectors where it could be used are immense, but that does not mean that it will replace the conventional manufacturing, because it still doesn't have that high production rate which the conventional manufacturing has. So this will be more useful for low volume, more customized part. So with that, I'll stop. I'll ask if there are any questions. I would be very happy to answer those.
Yeah, thank you very much, sir. Much informative session. Yeah, participant open for discussion. This session is open for discussion. Please unmute yourself and discuss. Otherwise, you may put the question in the chat box.
Yeah, good evening, sir.
Yes, please.
My name is Fahim, and I am a research scholar at Tewari Institute of Engineering and Technology, Patiala. So I'm working in the FDM technology, like I'm working with the PC, polycarbonate, and other materials, ABS and stuff. And I face the same issue like this because of these residual stresses. And the talk was very informative, and I got a lot of information from you. Thank you so much for that. And I get the same problem, like residual stress are there, and there are like the problem is defects like warping, or we can say curling. And I want to know a little, you can say about how can I just control that in that FDM printer, or during the FDM printing of this PC and ABS.
So essentially, there are two things to do. Distortions is what you don't want at the end. So the distortions could be mitigated in two manners. One is that you could build with a strategy where the residual stresses are such that they lead to nullifying the distortions. So imagine if you have this plate, let's say, and it's distorting like this. So you make it such that it will have residual stresses which will distort it the other way also. So you have competing residual stresses which lead to distortions on both the directions, thus nullifying the distortions. This is one strategy. However, this is not a very great strategy because it doesn't mean you don't have residual stresses. You still have residual stresses, but you have just made sure that they are annihilating each other, or rather compensating each other to not lead to distortion, but they have residual stresses. The other strategy is to mitigate the residual stresses to start with. And these are the two strategies which you can use. And you'll have to look at your specific problem and design as to which one do you want and which one can you do. It's not always possible that you can mitigate residual stresses. You will have residual stresses. You may not always be able to eliminate them. So it's a combination of what you want, what you can, is what you have to look at to decide what to do. We can discuss more specifically offline if required to look at your problem. But essentially, these are the two strategies. Any other questions?
Yeah, please, participants. Any other questions? Participants may put questions in chat box.
Hello, sir.
Yeah,
Yes,
sir,
please.
please.
This is Sinde from DKT College. I want to know that, sir, in metal 3D printing, so
Yeah.
surface finish, how we are going to control? Means here in FDM, it is in few mm to microns. So in metal printing, what about the surface finish?
That's right. So actually what we are doing is that we do machining finally. So you get the machined surface on top. And what we are installing, the machine which we are installing right now is a 5-axis CNC machine with additive platform. So it's a hybrid machine. It has a powder feeder. It has a wire feeder with a 3 kilowatt laser and has a 5-axis CNC machine. So you can add material, do additive manufacturing and do machining right there on the same machine. And the same NC code can be written. So some M codes will be for additive manufacturing and some will be for machining. And that's how you can make sure that you have excellent surface finish, not just on the exterior, but also on the interior. Imagine if you're creating a cup like this, you can machine it inside as well as you are adding material so that you don't have to have an accessibility issue. So, but these are all things which need to be done on a part by part basis. You have to look at what part you're manufacturing and you'll have to do that.
Yes, sir. Great. Thank you. Thank you.
Any other questions?
Good evening, sir.
Yes,
Am I audible?
Yes, you are audible.
Sir, my question is that earlier this morning, KP Karunakaran sir was there and you were shown an example of an impeller. Okay.
Oh, yes.
Which was done by laser cladding. So
Yes.
I would like to know more from you that when such types of staircase are being generated in case of 5-axis geometries. So
Yes.
I would like to understand whether in that case the stress which has been generated or the residual stresses which have been involved in those stresses, are those same in the direction or they vary with respect to the geometry of that? Because what happens when the material has been added altogether by layer, there is definitely once the first layer has been put up, and when the next substantive adjacent layer has been put up, there is a definite change in temperature, and this change in temperature definitely has some I don't know in depth, but you may be the right person to tell whether the change in the temperature definitely will be making some distribution in the stresses. So I would like to understand more when it comes to the machining part, because we are when it comes to the machining part, we only think about the additive out of the material. But when it comes to the actual insert machining with respect to the various tools, so when there is a change in the stresses, definitely the cost part regarding to the machining part is not been dealt or is not been talked about. So I would like to understand about the stress part whether the stresses in all the directions are the same or not. Means in the tooling geometry, I'm specifically talking about the cost in the tooling geometry.
Yeah, so actually the residual stresses will be very anisotropic. They will not be same throughout. So the 5-axis gives you the freedom of adding material in any way which you want. But with the same token, it also essentially creates residual stresses which are far more complex in its orientation. So the residual stresses are not same in all direction. And Professor Karnakaran is my senior colleague at IIT Bombay, and I very closely work with him on various projects. And so we both understand this, and we have worked a lot on residual stresses. We have filed some patents as well, which have utilized this specific anisotropy of residual stresses and anisotropy of growth in grains to our advantage. But you are right, it's a big challenge because the residual stresses will be anisotropic, and one needs to understand that much clearly to be able to use that and work with it. Some strategies which include, for instance, are to preheat the material. So you could actually have the laser heating done on the material before you start depositing. And that is one strategy which could be used. Apart from, of course, the other strategies which I talked about of changing the hashing strategy, changing the way you are providing power and things like that. But essentially, you have a lot more variables to play with. But that also is troublesome because you have so many variables to play with. You do not know what is the optimal. So it becomes a multi-dimensional optimization problem. And you may sometimes just end up in a local optima, and you may never get out of that because there might be a global optima somewhere else. But it's a challenge.
Sir, one more question. Is there, see, as you said, definitely there is an anisotropic of the material part. So I'd like to just understand whether the cost of, for example, if you're taking an example of an impeller, 5-axis impeller, so might be, you might have, for example, a cost for laser cladding, for example, 5,000 rupees for just to make this material. But I would like to understand more that if when it comes to the 5-axis machine, and if the residual stresses are too high, it might be you might land up machining, or the machining cost of the 5-axis impeller might be more than what is expected than in a normal machining it from a raw block. So does any work has been done in this direction?
So see, aerospace, you're right. So aerospace is all about cost of machining. So if you look at aerospace, you take a part, a block, and you create a small part out of it, and that part is usually less than 10% the weight of the original block.
Correct. Yeah.
So you machine 90% of the material out. Correct. So there's a large cost of machining involved in all aerospace components.
Correct.
So what additive can do is that additive manufacturing can produce a part which is very close to the final shape, and thus the amount of machining required is much less. So the cost of machining comes down drastically. However, what you need to make sure is that you relieve the stresses before you start doing all of this. So you essentially have to go through a stress relieving process.
Correct.
And so usually you do additive manufacturing by doing such a process control that you have minimum distortions, minimum residual stresses. But once you have created that, you take it forward, and then you further do residual stress relieving processes, heat treatments. And once that is done, that's when you do machining after that. And machining cost is certainly less because you have much less material to machine.
Fine. Yeah. Thank you.
Any other questions? Yeah, thank you.
Yeah,
Any other question?
Is there in the chat box you can refer to by G. Balasubramaniam. He says, sir, may I know, is there any institution from any of IIT or others from Pan India who are performing load acting thermal induced roller based research in LPBF technology to evade or reduce residual stress in build part?
So, well, Professor Karnakaran is one person who is doing some thermomechanical, processing at the time of additive manufacturing. But apart from that, actually, I'm not aware of. I'm not really aware of load acting thermal induced rolling based research on this. So I don't know. Maybe you'll have to do some literature search to see if that is there. There is another thing. If the research already initiated, then request you to provide some broad information on the same. Well, there's a lot of research happening 2 hours is not sufficient. A lot of other things happening during the, lot of calls coming and other things happening. So maybe what I would suggest is that those who are interested in this area, please visit us in IIT Bombay. Just let me know in advance so that we can create all the formalities of gate passes, and visit us in IIT Bombay and see what we are doing. And we are very happy to collaborate. We are open to collaboration. Of course, we still could only handle a smaller volume. We can't have hundreds of people coming, but we certainly would welcome you all to visit us to see what we are doing. Maybe we will be, we can organize a one-day workshop. Professor Karnakaran, I'll ask him to organize a workshop on additive manufacturing where you could come and have a look at all our facilities in IIT Bombay. Professor B. Ravi, myself, Professor Karnakaran, and there are some other colleagues of mine, Professor Mishra, who are involved in this process. So I think it's more prudent to do it that way rather than for me to talk about that stuff here. Okay, any other questions?
Yes, sir.
Hello, sir.
It is good to, yeah. Please go ahead.
Sir,
yes, please.
I'm Gopal Patil.
Yes, Mr. Patil.
KJ Engineering College, Pune.
Yeah.
So one question is that, sir, means not question, but it is a request to you that is there any chance for students who can visit our campus regarding 3D printing and design course?
So the answer is, like, you mean your students visiting us here in IIT Bombay?
Yes, sir. Yes, sir. Yes, sir.
So the thing is that it is possible. We can certainly design that. Now we have over 100 participants in this course. So we can certainly discuss this and take it offline and see. We will be happy to. We are a public university. We are a government organization. We'll be happy to have people come, and we can work it out. That's not an issue. I'm sure.
Yes, those who are looking forward to 3D printing and some innovation in that, so such students will be benefited. Such students will be benefited.
Certainly, we can. We all are students. I'm a student as well. So we all are.
Yes, sir.
Yeah, and we all are getting benefited and learning. So yes, certainly we can plan such a thing. Not an issue.
Yes, sir. Thank you, sir. Thank you.
Yeah, definitely, it will be wonderful. I have visited this RM lab when through one of the CEP course which Dr. Karunakaran sir has conducted, maybe 4 or 5 years back, and then he has shown all those like thermo. Using thermocol and all the process, ice and all, then different other processes like hybrid manufacturing and all. It will be wonderful. So the same thing I have discussed with Karunakaran sir, to have the CEP so that participant can come into the IIT and can visit and see all these facilities. Yeah.
Sure.
Yeah, thank you, sir. Thank you very much for the very wonderful session. You have a few compliments there in a chat box given by the participants. We can refer to all that also. Yeah. So,
all right.
Thank you very much, sir.
All right, then.
You organizers.
Yes, sir.
Have the concluding remark.
Yes, sir.
Yeah, please.
I'm glad to take this opportunity to give the summary and vote of thanks for this third session under the 3D Printing and Design FDP. I would like to thank eminent speaker for this session, Dr. Asim Tiwari sir, for his valuable time and deep insights on additive manufacturing algorithms. Sir started with an overview of the research work going on in his research group, which include a wide spectrum having 3D printing and of composites, smart factory, data analytics, and IoT research, ASM, that is additive subtractive manufacturing, fiber composite additive manufacturing, etc., among various others. Sir mentioned at the very start that special focus would be on enhancing understanding of residual stresses, since they can lead to cracking in additive manufacturing. Sir covered a case study on drilling-induced distortion, under which he explained the problem statement, mechanism of the process, microscopy and spectroscopy results, shortcomings, CAM issues, etc. So then briefed about basic equations of the continuum mechanics to back the understanding of the session topic. He explained the eigenstrains, that is any stress which has origin other than the elasticity. So I used the example of annealing to explain it further. So then highlighted the key aspects of formation of residual stress, under which he covered multiphysics modeling, explaining the development of residual stresses, so shed light on the 3D arrangement, effect of temperature and time on stress relief in welds, types of weld distortion. So then enlightened us on different ways of mitigating residual stress. He then gave an overview of finite element method with regards to thermal, structural, and welding modeling. Sir then gave an overview of process modeling, multi-layer additive manufacturing. He then talked about complexities of porosity and microstructures and elaborated further on many topics with excellent image demonstration. Lastly, sir highlighted the biggest disadvantage of 3D manufacturing, that is cost, and elaborated further on it. We are grateful to you, sir, for today's very enthralling session. I'm certain that all participants would reap great benefits from it. I would also like to thank all the participants for their enthusiasm and active participation throughout.
Yeah, thank you very much, Arundhati, for nicely.
Thank you, sir. Thank you.
With a nice concluding remark. So she is second year student, nicely concluded.
Oh, very, very nicely done, actually. Yeah, I'm happy to see that.
Yeah.
Thank you very much.
Thank you very much, sir. Thank you.
All right, I'll sign off now. Bye.
Yeah, bye, sir. Bye.